All right, everyone, we are back and we are going through our last problem, creep, creep, creep. So let's look at the deformation mechanism maps, label all the sections, rank yield stress, solute concentration, grain size. So I'm just going to do the first one. TS, dislocation glide, elastic. This is Nabarro herring. This is power law creep. And then this would be our cobalt. This would be our cobalt here. And then the same for the rest of the maps. Let's go ahead and rank yield stress. Yield stress of B is greater than yield stress of C, which is greater than the yield stress of A. Our cobalt creep is changing, so our dg of B is less than dg of C is less than dg of A. Solute strengthening, we're not really sure, because typically we think that what's causing this maps to change is work hardening and grain size strengthening, so I'm going to say C solute could be all equal for all of them. Excellent. Or they could be going simultaneously. There's an argument to be made, but I would say most likely it's going to be the same. What strengthening mechanism is going to produce the maps? So work hardening, so change of yield stress scales with dislocation density rho to the 1/2 power. Could be grain size strengthening, so dg to the -1. Stress strain curves. So we know same Young's moduli. One looks like this, one is going to look like this, one's going to look like this. And that's going to be B, C, A. There we go. I take material from B and I precipitate strengthen. How will the map change? How will the stress strain curve change? So it would get even closer and higher here. And if I precipitate strengthen this, probably a steeper slope, and it fails even earlier. So this is B, precipitate and strengthened. Excellent. Why does Nabarro herring dominate at lower temperatures than cobalt creep for Nabarro herring? So we can remember our Nabarro herring is equal to K Nabarro herring stress dg to the -2. And the key kind of factor here for the lower temperatures is d naught exponential minus Q lattice over KT. Q lattice activation energy is always greater than that for the grain boundary. So if I look at cobalt, stress dg to the -3, and we're moving, and actually minus Q grain boundary over KT, we're always moving faster in this diffusive component than compared to here. So in terms of when this region will dominate, because this exponential term, this term should dominate at lower temperatures because it's able to move faster because of that lower activation energy. So now, the weird part is, why would Nabarro herring ever dominate at all? And that has to do with kind of the picture of, as my grain size shrinks, I have more diffusive pathways, so I can diffuse in cobalt. But if I have a large grain size, eventually this wiggle over here will dominate the whole thing. So, yeah, we'll see you all. I'm looking forward to a much more thorough explanation. But, yeah, we'll see you all in the next video. Thanks. Bye.